Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Okay, so this is the recording lecture for chapter 6, that is sensors and transducers for biomedical system. Okay, so for this lecture, it will include the definition of the sensor, transducer, and actuator. And you will learn also the terminology and errors of the sensor, strain gauge, Wheatstone bridge, inductive capacitive, and temperature transducer. Okay, as the introduction, most medical instruments are electronic devices and so must have an electrical signal for an input. So when a biopotential must be acquired, some form of bioelectrode is used between the patient and the instrument. So that means you have learned in the previous chapter about the biomedical instrument block diagram. The general, that is in the measurement including the bioelectric or biopotential, and also the parameter from the human. So for the biopotential, bioelectrode is used. This means we use bioelectrode to get to change the biopotential to electric. This means to record it. And then for other parameter, other physical parameter, usually some non-electrical parameter, transducer is used to convert this parameter such as force, pressure, or temperature to analogous electrical signal proportional to the value of the original stimulus parameter. This means when you have to record the measurement, you need to use the electrode and transducer. Okay, definition of the transducer. A transducer is a device that converts some form of energy produced by a physical stimulus to another form of energy. This means the transducer is the electronic component that change some form of energy, for example, the temperature into another form of energy. Transduction is the process of converting the transducible property into electrical signal, then can be input to an instrument, because medical instrument only can read the electrical signals. That's why we need this transducer to change from other physical parameter into electrical signal. But in general, the transducer is from one energy to another form of energy. But sensor is a device that convert a physical parameter to an electrical output. That means only electrical. So there is called as sensor. But for the transducer, is changed to any kind of form, any form of energy. For example, it also can change from temperature to mechanical to magnetic, for example. So there is transducer. So transducer is the that means sensor is one of type of the transducer. Okay, and actuator is a device which convert an electrical energy to mechanical or physical output. So the opposite of sensor is actuator, because usually when you read about the sensor, usually it's relate to the transducer and actuator. So actuator is opposite form of sensor. So from electrical energy to mechanical. It's not opposite, but it is from the sources of the sources input is electrical energy, and then change to the mechanical or physical output. Alright, so as a comparison of sensor and transducer, sensor is detect, as I said just now, it's detect one form of energy and convert the data to electrical energy. On the other hand, for the transducer, it's convert from one form of energy into another form of energy. They say it is a bigger field. And a sensor is produce electrical signal based on the physical quantity that is detect. But for the transducer, it convert from one form of energy into another form. So the sensing element of sensor is the sensing element itself. But for the transducer, usually it is plus with any associate circuitry. So as a feedback, sensor measure quantity, but it cannot give feedback to the system. But for the transducer, it can convert between one form of energy. Therefore, it can provide feedback to the system. This is the basic block diagram. So when you measure the quantity, any quantity from for the medical instrument is from human, and then the transducer is actually including sensor plus the signal conditioning. So this is the basic block diagram of transducer. Alright, so for the sensor, this means for the sensor and transducer, the term can be interchangeable, but you need to understand that for the sensor, the output is electrical output only. But for the transducer, it can be any physical stimulus or any type of energy. So this active and active, so that means transducer or sensor can be divided into two basic category. That is active and passive. So the active sensor is the sensor that require external source to power the device. For example, the resistive strain gauge blood pressure require 7.5 volt to measure the pressure of this means the blood pressure. And passive sensor, it is provide its energy or derive its energy from the phenomenon being measured. For example, the thermocouple is one of the example of passive sensor. Okay, these are some of example of sensor and sensing element. So, okay, the sensor type is thermal. So the sensing element of the sensing element that you use is, for example, is thermocouple and thermistor. So it is used for electronic thermometer. And for the mechanical sensor, this means it's detect the mechanical changes, including the strain gauge, piezoelectric sensor. So it used for the pressure transducer. For the electrical, we use the electrode as we have learned in the previous chapter. So electrode is it can categorize as sensor. It's measure the electrical from the input. So it's used for the electrocardiogram and encephalogram. And for the chemical sensor, it's also use electrode. But for this chemical sensor, usually used for the pH meter. And optical sensor is use the sensing element of photodiode and photomultiplier. So it's used for the pulse oximeter. And okay, that one is the sensing element. So for the instrument, based on the instrument, for example, oral digital thermometer. Oral digital thermometer is to measure the temperature. So the sensor that used in the oral digital thermometer is thermistor. Okay, so this is the output and the range. And in the digital sphygmomanometer, it is to measure the blood pressure. So the sensor that used in the digital sphygmomanometer is stethoscope or strain gauge. So the output display is pressure. And to measure the blood oxygen, we can use the pulse oximeter. So the sensor in the pulse oximeter is photodiode. So it will represent the percent of oxygen saturation in SpO2. Okay, so this is the example of biopotential. So biopotential, it's used the electrode. So this is example of electrode used for several medical instrument. Alright, so in sensor, need to understand several error and terminology, including so for the sensor error, if the error is application error, it is error caused by the operator. And characteristic error is error generated by the devices, or for example DC offset. Dynamic error is the delayed response time. It is including the delayed response time, amplitude distortion, phase distortion. And for environmental error, it's including surrounding temperature change. For example, the error is caused by the surrounding temperature change characteristic of the sensor or component. Okay, so terminology in the several terminology related to the sensor is okay, first of all is sensitivity, where sensitivity is the minimum input of physical parameter that will create a detectable output changes. So if for example for the thermometer, what is the minimum input that will create the detectable output? So this is the sensitivity. And sensitivity error is the deviation from the ideal characteristic curve. So this is similar from the previous chapter. We have the gradient. So we have the ideal characteristic curve and so if the after we measure, it is different from the ideal characteristic curve. It is categorized as sensitivity error. And range is the range of the maximum and minimum value of applied parameter that can be measured. And dynamic range is it means we have the interval of the minimum value. And precision is the degree of reproducibility of the measurement, how the measurement is similar for different time of measurement. It means the value of the measurement should have similar value. So it is high precision, and the resolution is the smallest detectable incremental change of an input parameter that can be detected in the output signal. So it means usually for the resolution is for the video, but it's include that means the smallest changes, incremental change in the input. And accuracy is the maximum difference between actual or supposed value and the indicated value at the sensor output. So if the output, the measured output is similar, this means have similar value with actual value, so it is high accuracy. And offset is the output value that exists when it should be 0. So this is an example of the offset. So the we know that for the accelerating current, for example, it has curve like this. So that means we know that the middle value is the should be 0, but if it is not reach the 0, so we call the different value is the DC offset. And linearity is an expression of the extent to which the actual measured curve of the sensor depart from the ideal curve. So for the so we have this means for every medical devices we have the ideal curve, but if the actual measured curve is different with the ideal curve, we call it as linearity. And hysteresis is capability of the following changes of input parameter regardless of the direction. And the response time is the time required for a sensor output to change from its previous state to a final settled value with a tolerance band of the correct new value. So response time is the time required for the sensor. And dynamic linearity is the ability to follow the rapid changes in the input parameter. Alright, so this is the some terms related to the sensor. Okay, so for the transducer, we can from the input, this means from the measuring, there are several input. So the transducer can be divided into displacement. This means, for example, the displacement, temperature, capacitive, and inductive. So for the displacement transducer are typically used to measure physical changes in the position of an object. So it's usually detect the change in the length, pressure, or force. So that means for the pressure sensor is actually the displacement transducer. So variation in this parameter can be used to quantify and diagnose abnormal physiological function. Displacement transducer can be resistive, inductive, or capacitive. So this some example of the displacement transducer. So it's change the this means it's detect the changes of the length, pressure or force. Okay, so application of the strain gauge. Okay, one of the main example of the displacement transducer is strain gauge. So as example application of strain gauge, it's used for the respiratory monitoring, digital weight scale, feedback hand glove. So these are some example for the strain gauge used in the medical. And this strain gauge is produce the changes in its resistance proportional to the applied strain. So okay, so this means the strain is actually the changes of the elongation. So it's measure the displacement. So from the changes of the replacement, it will change the resistance. So this is the how strain gauge is function. Okay, so strain gauge are displacement type transducer that measure the changes in the length of an object as a result of an applied force. So strain gauge is a resistive element that produce a change in its resistance proportional to applied mechanical strain. So the strain gauge is changes in the resistance. So it's called as resistive element. So strain gauge is the force applied in either compression. So that means when we compress also have the changes of the resistance, and when we apply tension or we elongate it, so it's also have the changes of resistance. The piezoresistive effect describes change in the electrical resistivity of the semiconductor when mechanical stress is applied. So the changes of resistance when we apply displacement change, it's called as piezoresistive effect. Okay, so this is the detail of what is piezoresistive. Okay, so as shown in the figure, okay, we have figure A that shows a small metallic bar with no force applied. So it will have a length of L and a cross section of A. So when it's changed, the length changes in length are given by delta L, and changes in area are given by delta A. Alright, so okay, so for the figure B, it shows the result of applying a compression force to the end of the bar. So as you can see here, the force arrow is toward the bar. So it means we apply the force from the end of the bar toward the middle. So we compress it. So it have the changes of delta L here, delta L at the end of the bar. And also, okay, this means the changes of L is negative delta L. So that's why the this means the after the force, after the applied force, is become L minus delta L. But the cross section is increased. So A plus delta A. And if we apply the tension, it is opposite from what we apply in the compression. So how the strain gauge is function. Okay, because the formula for resistance for the metallic bar is given by the term of length and cross-sectional area. So we have the R equal rho times L over A, with where rho is the resistivity constant of the material in ohms meter, and L is the length of the length in meters, and A is the cross-sectional area in square meter. So you can, this means the R, the resistance that we usually measured before actually is based on the current length and cross-sectional. But the real property of the uh, of the material is actually given by the resistivity, because the resistance is actually depend on the length and the cross-sectional of the material. So the piezoresistivity is the change of resistance with changes in size and shape. Size and shape is called as piezoresistivity. So this means if the R, okay, so if the intention, the resistance will become R plus H, but in compression it's become R minus H, where H is the changes in resistance. So when force is applied, so it's will change based on the L and A. So this is the effect of piezoresistive. Okay, so there is the piezoresistive. There is the property of the material. They change with the changes of displacement. So usually the strain gauge is label. This means we indicate how we indicate the strain gauge sensor by gauge factor. So gauge factor is it provides sensitivity information. So the gauge factor will, from the gauge factor value, we can detect how sensitive the displacement sensor. So gauge factor is the delta L over R divided by delta L over L. So this is the gauge factor. So it is a unitless. So gauge factor is actually varies with temperature and type of the material. So it is important to select material with high gauge factor and small temperature coefficient for the displacement sensor. For common metal wire strain gauge made of constant turn, gauge factor is approximately equal to 2. And semiconductor strain gauge made of silicon have a gauge factor about 70 to 100 times gauge factor. And therefore much more sensitive than metallic wire strain gauge.